Hi everybody, we are now going to solve exercise 2, chapter on information asymmetries. So the competitive labor market is populated by workers with high productivity, type H, and workers with low productivity, type L. All potential employers would offer an hourly wage of 190 euros to a very productive worker and 130 to a worker with low productivity. The labor supply curve of highly productive workers is this one, while the one for low productive is this one. Okay, and W obviously is the hourly wage, as usual. Now, the first scenario we are given is the following. We have to suppose that the worker's productivity is an observable characteristic. So basically, employers enjoy perfect and symmetric information. Okay. Under this scenario, we have to answer point 1. So here we are in the scenario of perfect and symmetric information. Okay, that's the scenario. So we have to find the equilibrium in this case by specifying the salary offered to each type, so to both L and H, the number of L and the number of H hired at equilibrium. So in this case, since we have perfect and symmetric information, the firm knows if the worker is H or L type. So employers will offer a different wage to L and H workers. Okay? In particular, the wage offered to H workers will be equal to their marginal productivity, that in our case, we know this from the text, is equal to 190. While the wage for low productive workers will be equal to the marginal productivity of low productive workers, and this is equal to 130. Okay? So in this case, it's easy to find the equilibrium wages because the firm knows if the worker is L or H, so the firm will pay H MPH and L MPL. Now we want to find the number of workers hired at equilibrium for each type. So we have QH equal 0.1 times W minus 80. So we simply substitute and we have 0.1 times 190 minus 80, and this gives 11. And then we have, so 11 is the number of L workers hired at equilibrium. We now find the number of L workers as well, starting again from the supply function for L workers. We substitute, the wage is 130 minus 10, so this gives 12. And this is the number of L workers hired at equilibrium. Okay, and this is all for point 1, because we have found the equilibrium under this perfect and symmetric information scenario, both in terms of wage and in terms of the number of workers hired. Okay, and now we can move to point 2, where we are asked to graph the equilibrium that we have just found. Okay, and this is what we're going to do now. Okay, so let's graph this equilibrium. We graph it together. So let's graph it. So here you put Q, the number of workers, and here you put the wage. Okay. Then let's start with the demand, both the demand for L and the demand for H. We have here suppose this is 130, so basically MPL, and suppose here you have 190 MPH. Okay, so we just draw a line here, and this is DL. Okay, DL, and this up here is DH. Okay, so now we need to represent the supply curves. Okay, so let's write them in the inverse form to be able to represent them correctly. So let's start from the supply of L workers. We know it is 0.1 times W minus 10. So rearranging it a bit, we have 0.1 W minus 1. So we get that W is equal to 10Q plus 10. Okay, just computing the wage. Let's do the same also for H. We start from 0.1 W minus 80. So we get QH equals 0.1 times the wage minus 8. And so we get that the wage is equal to 10Q plus 80. Okay, we have to represent these two supply functions here in the graph here above. Okay, and this is what we do now. This will give the equilibrium. Okay, so suppose that number 10 is here. We represent now the first one. Okay, so we might have a function like this. Okay, so this is our SL here. And this equilibrium point here, so the intersection between SL and DL, corresponds to the number of workers, of L workers, hired at equilibrium, so 12. Okay? Now, the number of workers hired at equilibrium for L workers is 11, so it will be somewhere here. Okay? And this means that my supply curve for L workers must go through this point. So it's something like this. They should be more or less parallel. Okay. So this is SH, and this is basically 80. Okay, so this is the graph. And we have 11 and 12. Okay, and we have represented everything. Okay, so we are done with point 2. We have represented the demand for L, the demand for H, the supply for L, the supply for H, the equilibrium wages, and the number of workers hired at equilibrium. Okay, so now we move to point 3. Okay, so we leave this graph on the side for a moment, and we move to point 3. Point 3, everything changes because now there is a different scenario. Now potential employers cannot observe workers' productivity. So now we are under the scenario of information asymmetry. Asymmetries. Okay, because now employers do not know if the worker is L or H. Okay, so it is a different scenario with the one compared with the one that we have analyzed so far. Okay, and now the question is, if all employers are risk neutral, what hourly wage will be offered to each type? And again, how many workers will be hired? So basically, we have to repeat the same that we did for point 1, but under information asymmetry. Okay. So now, since they don't know if the worker is L or H, workers will offer, employers will offer workers the same hourly wage. So they will offer the same wage to all workers. So WL equal WH equal W now. They are all the same, okay? And this wage will be an average given by, weighted by the respective probabilities. So we need to find the probability that the worker will be H and the probability that the worker will be L. Okay, so to compute this equilibrium wage, we need to know the probability of the worker being H and the probability of the worker being L. Otherwise, we cannot compute this average. Okay. Basically, this probability corresponds to the percentage of highly productive workers and low productive workers as a function of the hourly wage offered. And this is what we do now. Okay. So first of all, we start with the fraction of H workers, so probability of H. So what do? We take the total amount of H divided by the total amount of workers, because it is a probability. So basically we take the favorable cases over the all possible cases. Okay, it's a standard computation of probability. Now here we substitute the supply functions. So QH becomes 0.1 times W minus 80 over the sum of the two functions. So 0.1 times W minus 80 plus 0.1 W minus 10. Okay. So we compute here a bit. We get here 0.1 W minus 8. And we can write it better as 0.1 that multiplies W minus 8 plus W minus 10. Okay. We can simplify here and we get W minus 80 over 2 times W minus 90. Okay. And that's the fraction of H workers. Okay. We now want to find the fraction of L workers, and we repeat the same reasoning. Okay, so now we compute the fraction of L workers. So fraction of L workers here. And again, the reasoning is the same. We take QL over QH plus QL. So in this case, we have QL, so 0.1 W minus 10 over the sum. So 0.1 times W minus 80 plus 0.1 W minus 10. We repeat exactly the same. So we just find a way to simplify. 0.1 times W minus 80 plus W minus 10. And so here it goes away and we get W minus 10 over 2W minus 90. Okay. Okay. You could also compute this probability as, you know, like considering the fact that the probability for H is W minus 80 over 2W minus 90, it's enough if you do 1 minus, you know, and you get this one. It's the same. Okay, at this point, finally, now we can compute the hourly wage, okay? Or at least we can write the function for the hourly wage, okay? So now we compute the wage offered by firms. Let's see. So we have this wage will be the probability that the worker is H type given by W minus 80 over 2W minus 90 times the wage in this case is marginal productivity, 190, plus the probability that is L type times the wage in this case, 130. Okay? Now we need to compute a bit. So we multiply both sides by 2w minus 90, and so we get 2w minus 90 times w equal 190 times w minus 80 plus 130 times w minus 10. 10, this is 10, okay? And now we compute and we have 2w to the power of 2 minus 90w equal 190w minus 15,200 plus 130w minus 1,300. It's an equation, okay? You still can write it better, okay? So summing up, you get 2w squared minus 410w plus 16,500 equals 0, okay? Just a matter of computation. We can simplify this. How? Dividing everything by 2, and we do this because the computations are easier, okay? So this is what we do now. So we go on and we divide everything by 2. Okay, and so we get w square. Okay, so now you can see, well, yes, w square minus 205w plus 8,250 equals 0. This is a second degree equation. We have to solve it. And the formula to compute the wage, we write wage 1 and wage 2 because it is a second degree polynomial equation, is this number here, 205, plus or minus square root of this number to the power of 2, that gives 42,025, minus 4 times 1 times 8,250, okay, divided by 2 times 1, so 2. So you get 205 plus or minus square root of 9,025 divided by 2. So you get 205 plus or minus 95 divided by 2, and you get 2 results. The first one is this one with the minus, and then the other one with the plus, the sum. So this gives 150 and this gives 55. Okay. Now, before going on, we have to check whether both solutions are fine. So, and meaning we have to check if both of them are higher than the reservation wages of workers. Okay, let me write this. Okay, we check if wage 1 equal 55 and wage 2 equal 150 are higher than workers' reservation wage. Basically, we know what the reservation wage is looking at the graph, okay? Because if you look at the graph, you see immediately that the reservation wage for the highly productive worker is 80. I put the graph so that you can see. You see 80. And for L is 10, so it is enough to check if it is fine for the H worker. If it is okay for the H worker, it is okay also for the L worker, okay? So, in particular, and now I write it here, okay? So, we check if 55 is higher than the reservation wage, we call it W0, of H worker. And this reservation wage, in our case, is 80 because it is given basically by the intercept. That's the reservation wage, okay? But in this case, 55 is lower than 80. So we can't consider this value. This value will never be accepted, okay, as a wage. So we discard the wage equal to 55. Let's see the second one. The second value is a wage equal to 150. This is good because it is higher than the reservation wage. So the wage, in this case, at equilibrium will be 150. That's the equilibrium wage, okay? And now, since we know that this is the equilibrium wage, we can compute how many L and how many H. And this is what we do now. Okay, so we now compute how many L workers. So now we know that the equilibrium wage is 150, okay? Now we find how many L and how many H by substituting in the supply function, okay, as usual. So we have that QH is equal to 0.1 times 150 minus 80, and this gives 7. And QL is 0.1 times 150 minus 10, and this gives 14. And we are done with point 3, okay? Because we were asked to compute this thing, okay? And we have done it. Okay, fine. Now, the last point, point 4, okay? Point 4, indicate in a suitable graph the loss of social well-being generated by the information asymmetry in the case of hidden information, okay? So basically, to do this, we have to represent the equilibrium found at point 3, okay? So we represent the equilibrium found at point 3 in the same graph, okay? So let's take here, okay? I change color so now you can see. Okay, so let's say that 150 is somewhere here. So this is D, total D, 150. Okay, so the intersection point between SH and this new demand gives the number of workers hired now at equilibrium, that's 7. While this intersection point here gives the 14. Okay? So now we have to indicate and also, only indicate in the graph the loss of social well-being due to this hidden, to this asymmetric information context that we have. Okay, obviously, we have two kinds, the deadweight loss that arises is given to actually two reasons. The first one is that you're hiring too few L because too few H, because before you were hiring 11 and now you're hiring only 7. So that's the first deadweight loss. So this is, let's call it deadweight loss 1. Okay, and then you're hiring too many L. and that's the second deadweight loss. Deadweight loss 2. Now we specify and we write everything, but that's the solution because we just had to indicate it, okay? But we write it with more details. So basically, deadweight loss arises for two reasons. The first one is that too few L are now hired, in particular 7 instead of 11, and too few H are hired, and too many L are hired, basically 14 instead of 12. Okay, this is deadweight loss 2 in our graph. This is deadweight loss 1 in our graph. Okay. And this gives basically the deadweight loss under this scenario. And we are done with this exercise.